Okay, let's unpack this. For the last couple of years, the excitement around AI hasn't just been about massive large language models, but about their extremely powerful specialized cousins, the large reasoning models, or LRMs.
Exactly. These are the systems that have been fine-tuned, often using, pretty sophisticated incentive structures like reinforcement learning with verifiable rewards, specifically to generate solid, step-by-step argumentation. The promise is incredible.
The promise is genuine generalized reasoning.
Exactly. Across really complex domains.
And we've been told these models, DeepSeek R1 or some of the powerful specialized ones like GPT-4o, are on the verge of solving hard problems in math, in abstract physics, even complex legal arguments.
Hmm.
And I mean, if you look at many of the existing benchmarks like NLGraph, their performances, it's near perfect.
It looks extraordinary, yeah. But that's because most of those legacy benchmarks, they're testing problems with, let's say, modest complexity.
Yeah.
The average path length in some of those famous data sets is bounded. Sometimes it only needs a look ahead of like 1.8 steps.
So they're basically simple logic puzzles, relatively speaking.
You got it.
But the mission today is to dive deep into some new research. A study using the Deep Reasoning Dataset, or DeepRD, that really challenges this whole perception of generalized omniscience. The researchers wanted to know, does this success actually generalize when the problem gets way, way more complex?
And that's the key question, right? Because complexity scales up constantly in the real world. We're moving beyond simple deductions to the kind of, well, monster tasks that real-world reasoning needs. The paper even cites this one terrifying example.
Oh, yeah.
A single multi-hop Q&A task in Wikidata 5M that demands a chain of 177 distinct reasoning steps.
177.
That's the true scale we're talking about.
And that's why they built DeepRD. They use this sophisticated generative process to create tasks. But the key thing here is that the complexity is controllable and unbounded. They can make problems far harder than anything the models would have seen before.
Okay, here's where it gets really interesting. Because to measure the limits of reasoning, they had to go beyond just counting tokens or nodes in a graph. They came up with two key metrics: look ahead, which they call L, and number of branches, B.
Let's start with L, look ahead. This is a crucial idea they introduced to avoid what they called the clever Hans cheat.
Go what now?
The clever Hans cheat. So if you just measure the total length of a path, say 100 steps, a model can look smart without doing any real reasoning if the path is just a straight line. The next step is always obvious.
So L isn't about the distance, it's about the difficulty of the decision at each step. Precisely. L measures the number of breadth first search BFS iterations you need just to figure out the very next correct step. Think of it like a chess engine. A chess engine doesn't just care how many moves are left. It cares how deep it has to look right now to know this move is the right one. That's L.
That makes perfect sense. So a high L means the model has to hold this really complex temporary search in its head just to justify the very next move.
Correct. And then you have B, the number of branches, which is sort of the width of the problem. B is just the number of immediate choices you have from the start node, the fan out.
So L is depth, B is width.
You got it. And if B is large, the search space just explodes. Random guessing becomes, basically useless. So we're really measuring the fundamental difficulty of the search and the decision-making.
And when you actually test these models on their ability to handle a deck search, L, across a wide set of choices, B, the findings are. They're pretty shocking.
They really are. The core result on symbolic graph tasks is just unmistakable.
Right.
As the look ahead, L goes up. The performance of all the models, LRMs like DeepSeek R1, even GPT-4o, it just drops abruptly. And it collapses completely to 0% accuracy.
Zero. Not like 10%. Zero. Even for GPT-4o. So you're not talking about a slow decay. You're saying it hits a hard wall.
A wall. It falls off a cliff. It really speaks to the fundamental brittleness of the system when it's dealing with complexity it hasn't seen before. These models are amazing interpolators. They're brilliant inside the complexity zone they were trained on.
But the second you step outside that,
they don't fail gracefully. They just stop working as a reasoning engine.
And the number of branches B, that just makes the cliff appear sooner.
Absolutely. The wider the choice space, so a larger B, the sooner the performance collapses. You compare B equals 2 with B equals 16. The B16 test just falls apart at a much, much smaller L. It's like the model gets overwhelmed almost instantly.
Now, someone listening might think, okay, this is just a problem with cold, abstract symbols. What about messy, human, natural language? Did they check that?
They did, and the answer is a clear yes. when they translated these same complex graph structures into natural language proof planning tasks. So asking the model to predict the next logical sentence, the same performance cliffs were there.
And were they worse?
In some cases, yes. They happened at even lower complexities. For the specialized LRMs, the collapse in just predicting the next step starts happening between an L of 16 and 64. It seems like the reasoning is even more fragile in a language environment.
Let's talk about the failure itself, because you said it wasn't always some big mistake at the very end of 100 steps.
That's right. And this is a really profound insight. They looked at the thinking traces from DeepSeek R1 and found what they call propagation error.
Yeah.
The failure is usually a small local mistake really early on,
How early?
like within the first few hops. Maybe the model misses an edge that was actually there, or, and this is a big one, it hallucinates an edge that doesn't exist.
Okay, so it's like if I start a math proof by saying 2 + 2 = 5, every other step I take might be perfectly logical based on that first mistake.
But the final conclusion is guaranteed to be wrong.
Because the foundation is flawed.
That is the perfect analogy. The LRM keeps reasoning in a way that's locally consistent, but it's on a path that's based on a faulty premise. So the error just propagates, and it ends up with the wrong answer, or it just says, no path found.
This brings us to the big counter-argument you always hear when models fail on long chains. It's just the token limit. The context window, the model forgets. Did this research debunk that?
It did, and this part is so important. First, they just looked at the data. The LRMs rarely even hit their context limits. In fact, in a lot of the high complexity failures, the token usage actually went down because the models got lost and gave up early.
But the real killer experiment was the chain graphs.
Yeah.
D = 1.
Yes. This is brilliant. They made the easiest possible reasoning task that was still incredibly long, a chain graph. By setting B to 1, there's no branching. There's only one choice.
So the look ahead, L, is always 1. The next step is trivial.
Always trivial. The only thing they changed was the total length, the depth, and they pushed it all the way up to 1,536 steps.
Which is just a ridiculously long, simple chain. Why that number?
They wanted to push way past any known context limits or what you typically see in training, and they found that even on this extremely simple reasoning task, the models still quickly drop in performance at great depths.
Wow.
It was devastating. It showed they can't even reliably track progress over a long, linear, logically trivial task.
So this confirms it. It's not the context window. It's not a failure of some complex search. It's a failure of fundamental generalization. They can't maintain the internal state required to track coherence when the task is longer than what they've seen, even if it's dead simple.
Exactly. And the final nail in the coffin was this. When they just gave the nodes to the model in the correct order, basically asking it to read a correct proof, it got near perfect performance.
So it can follow along, but it can't generate the path itself.
It can process and verify a long proof, but it can't reliably generate or track one internally over those same lengths.
So connecting this all back to the real world, what does this mean for applications?
Well, we have to be fair. First, there's a lot of utility. The researchers looked at huge real-world graphs like ConceptNet, and they confirmed that the vast majority of tasks do fall inside the LRM's success regime, low L and low B.
Okay, so for most common everyday stuff, they're great.
They're excellent. But the danger is in that long tail of difficult problems.
The edge cases.
The really hard instances, the ones where we actually need superhuman reasoning, those fall squarely outside what these models can do. For this huge knowledge graph, Abulhair 2, an example with a look ahead of 100, is only in the 99th percentile of difficulty. But we know LRM accuracy collapses way before L gets to 100.
Meaning the most critical, challenging problems in science, in medicine, in law are the very cases where we can predict a systematic failure.
Precisely. And in natural proofs, which is a corpus of real-world written proofs, the complexity that makes these models fail, around an L of 60 to 32, that corresponds to the 50th and 75th percentiles of proof length in the real world. This isn't just an abstract limit on some weird synthetic task.
It's happening at intermediate difficulties in the wild.
Yes, that inability to solve the crucial complex 1% introduces a massive systemic risk if we start relying on these systems for high-stakes decisions.
So to wrap this all up, the key takeaway from the DeepRD study is that current large reasoning models are fundamentally brittle. They hit a wall and collapse to zero accuracy once reasoning complexity gets past a pretty modest threshold. They're, tightly bound to what they saw in training.
And bridging that gap is going to require totally new methods. We need to encourage robust, out-of-distribution generalization. The good news is the DeepRD generator is now available, so researchers can start fine-tuning and testing models specifically on these harder problems to see if they can fix this.
So what does this all mean for you as you watch this all unfold? We've seen two really distinct failure modes here. The failure on the hard search tasks, the high L, high B stuff suggests the models just don't have a good search strategy. But then the failure on those dead simple B equals 1 chain graphs, that's just a problem with memory and internal coherence. So given that evidence, what is the most critical missing ingredient for the next generation of these systems? Is it fundamentally about better memory management over long contexts, or is it about injecting the foundational ability to learn a robust search strategy? Which area needs research funding the most to prevent these catastrophic collapses? That's something for you to mull or explore on your own.